So good morning, everybody. So I will start with some thanks to Filippo, to Francesco, to Vittorio for the nice conference and nice dinner yesterday night. So I realized that I didn't drink so much because I recognized walking back this bridge yesterday night. So okay, so comparing with the title from the program, so I added here the notch, because all our tests are done on and our results are obtained on notch specimens. I also want to say that this lecture is in memoriam of two great men, and I start with Professor Paolo Lazzarin. He was professor here in Vicenza. He's well recognized on notch mechanics, notch stress intensity factor, local strain energy density methods that he developed. I met him several times in different events, different conferences. I can say that he was a very kind man, very supportive, mostly for the young researchers. He also was the editor-in-chief for Fatigue and Fracture of Engineering Materials and Structures. And the other, also related to strain energy density, is Professor George Sich. He passed away last year. You know, he's outstanding researcher, one of the founders of fracture mechanics. He has two criteria in mixed mode fracture mechanics. Is the maximum circumferential tensile stress, MTS, of Erdogan and Sich back in '63. And later, 10 years later, he came with minimum strain energy density criteria. I also met him several times. I was invited by him in 2017 in Beijing to an international workshop. We stayed there 10 days in the same hotel. We shared the meals and we we visited some places in the University of Architecture and Civil Engineering. So he was also a great man. So coming to my talk, so I will say something, not too much, about additive manufacturing processes for polymers. Why to apply structural integrity for additive manufactured components. I will shortly present some methods, modern methods that can be used to assess the failure and the fracture of the additive manufacturing components, theory of critical distance, failure assessment diagram, and average strain energy density, and finally some conclusions. So coming to the processes for additive manufacturing of polymers. So what we can see, we have a large variety, maybe more than for metals or for ceramics. So, and we have different groups of methods, differ the state of the material. So the material can be powder for power bed fusion, can be liquid for vat photopolymerization or metal jetting, or can be solid materials for fused deposition modeling, basically for material extrusion and sheet lamination. Also, we have a variety of materials that can be used, polyamides, epoxy, and acrylate photopolymers for the vat photopolymerization methods. Usually for material extrusion, we have PLA, we have ABS, PETG. Acrylic photopolymers also for material jetting, and PMMA and PVC for the sheet lamination. What differ from this group of methods, different the principle of this. So we have selective fusion and solidification for power bed fusion. We have light reactive photopolymer curing for vat photopolymerization. We have extrusion of melted material and then solidification for material extrusion methods. We have material jetting of melted materials and solidification, later and ultraviolet curing. And we have lamination of sheets through thermal or chemical bond. So this is an overview. I will present, in my presentation, I'll present some results only for the red ones for digital light processing and fused deposition modeling techniques. We have results also for power bed fusion, quite a lot of results on SLS, but due to time, so I will limit it to this. So fused deposition modeling, it's a very known and used now technique, is probably the cheapest one. And the dimension and the technology improve, and the dimension of the components that can be 3D printed with this technology are higher and higher. So basically, the material is heated. It's heated. It's extruded and extruded on the print bed of the printer. So the main advantages is the cost, which is quite low, the possibility to have different types of materials, and the, let's say, user-friendly technique. We have some disadvantages. From this disadvantage, we can say that what we get, we have an anisotropic mechanical properties. We have limited surface finish. We have some problems with the dimensional accuracy, pure fatigue behavior, and sometimes for complex geometries, we need to add some supplementary supports. The other technique that I will show you the results today is the vat photopolymerization, which is use a liquid resin which is placed in a vat and then is selectively irradiated and solidified using two technologies. One is stereolithography, which is a moving laser which solidify layer by layer, or digital light processing. It's solidifying on one shot using a LCD, usually an LCD. The advantages of this, it's fast, it has very, very good resolution, and also allow multi-material printing. As a disadvantages, so we need the post-treatment, a cleaning and the curing post-treatment. We need some expert users are required because these resins are toxic, and the manipulation of them should be done with care. Okay, why to apply structural integrity to these components? So first of all, I mentioned already, so these techniques differ from the traditional processing techniques that not all the material is melted and homogenized. The ion processes of depositing layer by layer of polymeric materials results in anisotropic properties, sometimes introduce residual stresses, and can be some issues related to structural and to fatigue problems. The mesostructure of this, and I will show you some other pictures. So we can have voids in the structure of the even if we select 100% infill. We have sometimes low quality of the surface, scattering the dimensions, dispersion of data, and the variability of lifetime. So what is important now, because people tend to manufacture bigger and more complex geometries, what is the very important, and I will touch this problem in my presentation. We have a series of notches for the complex geometries, and also increasing the size of the components, we need to take into account the size effect. So I ask also, like all my students today, I asked ChatGPT to give me a definition of the structural integrity in additive manufacturing. And he says, very nice, it's the structural integrity provides a bridge between additive manufacturing innovative technologies and real-world applications. So when we go to real world, we need to take into account all these issues, because a part of to be able to manufacture this, what we are manufacturing should be safe, should have enough durability, and should be certifiable to service life. Okay, so if we look on the failure of additive manufactured components, we can categorize this in different, let's say, causes. We have the material ones, where we have results anisotropy, viscoelasticity, also age degradation. We have some manufacturing issues, which is the presence of the void, lack of fusion, raster orientation, and we have the design issues, which can cause very sharp corners or thin walls or some misalignment for application of the load. Just few examples. So these are some specimens done by SLS, selective laser sintering. The material is PA 2200. It's a layered structure. So when we did 3-point band classic test on beam, unnotched beam, but even on notch beam, sometimes the failure occurs as a delamination, which probably is due to the shear, transversal shear, and this is a competition between fracture on tensile, the lower fibers, and the delamination of between the layers. Also, when we tested some semicircular band specimens in 3-point band with different orientation of notch in order to look on the mixed mode, so we also sometimes have this delamination. So layer delamination it is one issue. Also for the SLS technique, we can have lack of fusion, so not all the particles are completely bonded to the near ones, and sometimes we can have this lack of fusion, which has important effect on the integrity of the structure. Coming to FDM technique, so this is a study published a few years ago in polymer testing. So looking on the presence of voids and the influence of the nozzle temperature on this, we can see that at lower temperature, 210, we have big voids, and then these are decreasing with increasing the nozzle temperature. It's true that the nozzle temperature should be adapted to the material that we are printing. Also, on additive manufacturing of using FDM, we have this influence of the raster orientation. So the failure follows somehow the angle of the raster, and you can see here 30, 45, 60 degrees, 90 degrees. So only at 0 degrees we can say that each layer takes strength. On the other side, so we have for 90 degree, for example, we have delamination between layers. These are also some results. We did some I showed yesterday. We did some shear tests, and here again the delamination, the orientation of the raster orientation influenced the shape of the failure of the ligament on the specimen. Also, for 90 degree, we get delamination. Okay, so having this, we try to find some methods to assess the integrity of such a structure. So one of the options is the theory of critical distance, developed by or proposed by David Taylor in 2007. He has a very famous book. And then later with Lucas Usmel and other co-workers, they propose that they assess that the fracture occurs at a particular distance where the stress take the value of an inherent stress. So the effective stress, which for tensile is the maximum principal stress, when reach an inherent stress at a particular distance, this distance depends on the fracture toughness and on the inherent stress. For brittle materials, this inherent stress is equal to the ultimate tensile stress. This theory of critical distance has different variants. So we have the point method, when the evaluation is done at half of the critical distance. Here we can assess the effective stress and compare it with the inherent stress, or we can integrate it on a line or on a specific area. To implement this method, so I mentioned we need tensile test results because we need the ultimate tensile stress. We also need fracture toughness, so we need fracture mechanics test. With this data, we can evaluate the inherent stress, can be equal with ultimate tensile stress for the brittle materials. We can calculate the critical distance, and then using a linear elastic finite element analysis, we can plot the maximum principal stress, and then at half of the length, we can get the effective stress, and then to predict the load where this occur, and to compare with the experimental data. We did this. Another method is to determine the critical length is to plot the stress variation near notch or crack for two different geometries with notches. Even one could be on tensile, but on this case it's a straight line here. And then we can get from the intersection of these two stress distributions, we can get the critical length and also the inherent stress. So the first application of this method to additive manufacturing component was were some papers of Lucas Usmel with some of his PhD students. They considered several 12 different notched geometry loaded in tensile or in bending. They use the FDM to build PLA filament. They use 240 temperature of the nozzle, 60 degrees temperature the build plate. They consider a layer thickness of 0.1 millimeters, 100% infill density, and for different shells of the specimen. So they produce the specimen with contour and without contour, with different sizes and without contour, and also they consider different raster angles. So looking to the error, which is the effective stress compared with the ultimate tensile strength, the relative error on the fracture stress, all their data for all the specimens and all combinations are mostly between minus to plus 20%. We did the same. We use our data, so we perform some 3-point band and 4-point band stress on single edge notch band specimens. It is other printers, so we have other material manufacturing parameters. These are built plus minus 45 degrees orientation of the infill and 100% infill, layer thickness of 0.5. So we take the value of the critical length proposed by Ahmed and Susmel, and we process our data and apply with this, but considering our ultimate tensile strength, and all the data for 3 different orientations are between, let's say, 11%, so below 20%, which shows that this method, the theory of critical distance, can be used on this type, and is not so sensitive to manufacturing parameters, because we use the critical length value that was determined on other tests with other publication parameters. We also apply this method to DLP manufactured specimens. So we use a commercial Anycubic printer with an LCD. We use 2 different resins, commercial resins, and for this we did the tensile strength test, we did the fracture toughness test, we identified the maximum tensile strength, we identified the strain at fracture, and then we calculate for different. You can see here for one resin we consider 2 exposure time for printing, and we have different tensile strength, we have different fracture toughness values, and we have different critical distance. So we try to look if the manufacturing parameters influence this value. So we did some tests using semicircular band specimen loaded symmetrically. We have different notches. The notches were directly manufactured, sharp notches and round notches. And in order to look on the size effect, we consider 4 different types of radius of the specimens from 10 millimeters, sorry, from 10 millimeters to 40 millimeters were the tested geometries. Initially, we compare our data with the classical strength of material theories for brittle materials, which is the maximum principal stress and maximum principal strain. So, as you can see, a part of some data for the biggest specimen diameter. All the others are rather conservative, considering maximum principal stress, or non-conservative, considering the maximum principal strain. So we apply the theory of critical distance, and with this, so we have determined K1C and the ultimate tensile strength. We calculate the critical length, and using the theory of critical distance, we come somehow between plus minus 20 degrees and between the classical strength of materials theories. This was for trans-green resin. For the aqua blue resin, results are also good using theory of critical distance, comparing with the maximum principal stress, which all are very, very conservative. Okay, so having these specimens with different radius, we try to look on the size effect. First, we start to interpret the Bajan criteria, which he's saying that the size effect, it's a asymptotic match between the strength criteria and the linear elastic fracture mechanics. And this curve, if we look on the logarithm of nominal stress to the logarithm of one of the dimension of the specimen, has this relation. The problem is that the 2 fitting parameters should be determined. So this was the reason that when we do the test, we keep constant the thickness of the specimens, and we vary only the radius of the specimens, and the crack length was approximately 0.5 of the radius. So we do the test. We calculate the maximum load, the bending moment, the nominal stress given by the bending, and to obtain these fitting parameters, we plot 1 over nominal stress at power 2 in function of the dimension of the specimen, the radius of the specimen. We try to apply a linear regression here and to obtain these parameters. So these are the experimental results and the asymptotic approach in this slide. So almost all the data, a part of one data for the smallest specimen with the radius 1, are more following the linear elastic fracture mechanics, so singularity stress field, rather than the strength of material criteria, which we need to take into account when design such structures, to take into account if we have notches to apply or to do the design according with the linear elastic fracture mechanics. Another let's say interpretation of the size effect is based on the Kitagawa-Takahashi approach, where they plot the nominal stress to ultimate tensile stress function of the ratio between crack or notch length to the critical length. If we do this for these 2 materials, trans-green, for these 2 resins, which are, let's say, quite brittle, what we can see that almost all the data are below the nominal stress up to, let's say, 0.2 of this. So for all notch specimens with round notch and with sharp notch. So another failure criteria is the failure assessment diagram, which try to be more general, combining brittle materials with ductile materials. So we have here, this is for cracked components. We have the ratio between stress intensity factor and the material toughness, and the stress and the yield stress. We can have, if kappa r is 1, we have brittle materials. If sigma r is 1 and kappa r is, we have completely ductile materials. So inside of the failure assessment diagram, we are in the safe zone, and outside in unsafe zone. So there are some adaptations for notched components. Cicero was one of the researchers from Spain to introduce this. They consider notch radius here and the critical distance again. And you can see their results are all in the experimental results for additive manufactured components. They use different orientation of the raster orientation, 0, 90, 45, so minus 45. They calculate the fracture toughness of the material, taking into account the radius of the notch, and they assess quite good that the fracture occurs on these specimens. The last method, I will go very shortly on this, probably coming from here, from Vicenza, I don't need to say too much about SED. We did some tests. So we did some tests, and I want to show you only the results. So we manufactured some notched components made on PLA and PLA plus carbon fiber. We use our printer in Timișoara, and we consider 4 different geometries, notched geometries with sharp notches of 30, 60, 90, and 120 degrees. This work was done by one of my PhD students, Esther Avălian. She was in Trondheim at that time. Filippo and Pietro were there. She worked there. They do the tests there. We have here the low displacement curve for the PLA and PLA plus carbon fiber, and then we apply the strain energy density approach. We use the equivalent material principle in order to determine the critical value of the strain energy, and then if we compare with the experimental data, made the critical load, we can see that we are also in the plus minus 20 degrees between the predictions and the experimental ones. What I would like to say about this, so surprisingly, all the properties for PLA reinforced with carbon fiber, all the properties were below the pure PLA, and only the area below the curve, so the fracture energy was higher. So we did the same for the PLA plus carbon fiber, and this average strain energy approach looks to work well in predicting the critical load. So, how much time okay. So I go to conclude. So I try to show you some results on notch and size effect in additive manufactured components. I think all these methods, TCD, average strain energy density, FAD, represent very useful engineering tools when we want to investigate the notch effect and the size effect of additively manufacturing components. just a point here, all these methods were developed for homogeneous materials. So additive manufactured components are not homogeneous at all. They are all, you saw, layered structures. And this is a, let's say, a good point that we can conclude that we can apply this even for these additive manufactured components. I know there are some results on applying the set for metallic additive manufactured components. The notch effect approaches are also reliable. Kitagawa, Takahashi could be used. And also we have, I didn't put here, we have predicted the fatigue curves using average strain energy density for the same combination PLA and PLA reinforced with carbon fibers, and looks also well for the fatigue predictions. I would like to thank to my colleagues, to Filippo and Pietro, and to Professor Susmel from Sheffield. And thank you very much for your attention.